indices and logarithms. We've already learned that 3 raised to power 5 means 3 times 3 times 3 times 3. 2 raised to power 4 is 2 times 2, 4 times. The superscript numerals 5 and 4 are called indices. In singular, it's called an index. In general, if n is equal to a raised to x, then a raised to x is equal to a times a times a x times. For example, 16 is equal to 2 times 2 times 2 times 2, which is equal to 2 raised to power 4. 81 is equal to 3 times 3 times 3 times 3, which is equal to 3 raised to power 4. 125 is equal to 5 raised to power 3. We can represent this information on a tree diagram as shown below. Laws of indices. Rule 1. Multiplication. When index numbers with common bases are multiplied, we simply add the index or the powers. That is, 2 raised to power 4 times 2 raised to power 6 is the same as 2 raised to power 4 plus 6, which is 2 raised to power 10. 3 raised to power 5 times 3 raised to power 2 is the same as 3 raised to power 7. 4 raised to a third times 4 raised to a third is equal to 4 raised to 2/3. In general, a raised to n times a raised to m is equal to a raised to m plus n. Rule 2. Division. When indexed numbers with common bases are divided, we simply subtract the powers. That is, 3 raised to power 5 divided by 3 raised to power 3 is equal to 3 raised to power 5 minus 3, which is equal to 3 raised to power 2. 4 raised to power 7 over 4 raised to power 2 is equal to 4 raised to power 5. In general, a raised to n divided by a raised to m is equal to a raised to n minus m. Note that the bases must be the same. Otherwise, the multiplication cannot be done through addition of the powers. That is, 3 raised to power 4 times 2 raised to power 3 cannot be simplified further. Rule 3. Power of 0. Any non-zero number raised to the power of 0 is 1. That is, 10 raised to 0 is equal to 1. 25 raised to 0 is 1. A raised to 0 is 1. X raised to 0 is 1. Rule 4. Negative indices. A number raised to a negative index is the same as the reciprocal of the equivalent positive power of the same number. That is, x raised to negative a is equal to 1 over x raised to a, meaning 2 raised to power negative 5 is equal to 1 over 2 raised to 5. 5 raised to negative 5 is equal to 1 over 5 raised to 5. The reverse of this is also true. That is, 1 over x raised to negative a is equal to x raised to a, meaning 1 over 2 raised to negative 3 is equal to 2 raised to power 3. 1 over 4 raised to power half is equal to 4 raised to power half. Rule 5. Powers of powers. When a number is written in index form and it is raised to another power, the indices are multiplied. For example, 2 raised to power 3 in bracket raised to power 2 is equal to 2 raised to power 3 times 2 raised to power 3. We add the powers and we get 2 raised to power 6. We could rather have done simply as 2 raised to power 3 times 2, giving us straightly to 2 raised to power 6. 4 raised to power 6 into bracket raised to power 4 is equal to 4 raised to power 20. Generally, if x raised to m in bracket raised to n is equal to x raised to power m times n. Note that all numerals multiplied or divided together in a bracket are raised to the power of that bracket. That is, 2 times 3 into bracket raised to power 4 means 2 raised to power 4 times 3 raised to power 4. 3 times 5 raised to power 2 is equal to 3 raised to power 2 times 5 raised to power 2. 2 over 3 raised to power 2 is equal to 2 squared over 3 squared. 7 over 9 raised to power third is equal to 7 raised to power third over 9 raised to power third. Generally, x times y to power m is equal to x raised to m times y raised to m, and x over y raised to power m is equal to x raised to m over y raised to m. Rule number 6. Fractional indices. Consider 4 raised to power half times 4 raised to power half. This is equal to 4 raised to power half plus a half, giving us 4. Also, root 4 times root 4 is equal to 4. Considering equation 1 and 2, it follows that 4 raised to power half is equal to root 4. 3 raised to power half is equal to root 3. Equally, 5 raised to a third times 5 raised to a third times 5 raised to a third is equal to 5 raised to a third plus a third, giving us 5. Also, cube root of 5 times cube root of 5 times cube root of 5 is 5. Considering the above two equations, it means that 5 raised to a third is equal to cube root of 5. Generally, x raised to power 1 over n is equal to nth root of x. Simple equations involving indices. For example, find x in 3 raised to power x is equal to 9. In our solution, express the right-hand side in index form. That is, 3 raised to power x is equal to 3 squared. Since the bases are similar, we equate the powers, and therefore x is equal to 2. In another example, 3 raised to 2x minus 1 is equal to 9 raised to 2x plus 2. In our solution, 3 raised to 2x minus 1 is equal to 3 raised to 2 times 2x plus 2. Equating the indices, we have 2x minus 1 is equal to 4x plus 4, and x is minus 5 over 2. Logarithms. We have seen how to write numbers in index form. When a number is expressed in index form with 10 as the base, the index is called the logarithm of that number. For example, 1000 is equal to 10 raised to power 3. 1000 is the number, 10 is the base, and 3 is the logarithm, abbreviated log. This is written as log to base 10 of 1000 is equal to 3. Similarly, log to base 10 of a million is equal to 6. Equally, 1 over 100 is the same as 1 over 10 raised to power 2, which is equal to 10 raised to power negative 2. Therefore, log to base 10 of 1 over 100 is equal to negative 2, which also can be written as log to base 10 raised to negative 2 is equal to 2. Logarithm tables. Mathematical tables give the values of logarithms of numbers to base 10 only for numbers between 1 and 10, but 10 excluded. For example, when we say log 3.25 is equal to 0.5119, we simply mean that log to base 10 of 3.25 is equal to 0.5119. Also, 10 raised to power 0.5119 is equal to 3.25. The logarithms of numbers between 1 and 10 are read directly from the tables. Logarithms of numbers greater than 10. Consider log 325. We first write the number in standard form, which is 3.25 times 10 to power 2. We then get the logarithm of 3.25 and logarithm 10 to power 2 separately. That is, log 3.25 is equal to 0.5119 and log 10 to power 2 is 2. We then add the logarithms, and therefore we have 2.5119. Thus, log 325 is equal to 2.5119. Equally, log 53.57, we shall have 53.57 is equal to 5.357 times 10 to power 1. Log 5.357 is 0.7290. Log of 10 to power 1 is equal to 1. Therefore, the log of 53.57 is equal to 1.7290. Logarithms of numbers less than 10. Consider log 0.00325. We write the number in standard form first, that is 3.25 times 10 to power negative 3. Find the logarithms separately and add the results. Log 3.25 is 0.5119. Log of 10 to power negative 3 is negative 3. However, the negative is indicated on the top of the number, that is 3 bar. This is called a bar number. Thus, log 0.0025 is equal to negative 3.5119. Note that the whole number is called a characteristic. The decimal part is called a mantissa. Anti-logarithms. Anti-logarithm is the inverse of logarithms. This is often read from the tables of anti-logarithms. If log 2 is equal to 0.301, then the antilog of 0.3010 is 2. Multiplication using logarithms. When we multiply numbers, we simply add their logarithms. For example, 2 times 4 can be calculated as log 2 plus log 4, which is 0.3010 plus 0.6020, giving us 0.9030. Now, to get the actual number, we get the antilogarithm of our answer, that is, antilog of 0.9030, which is 8. Division using logarithms. In division, we simply subtract the logs of the respective figures. Example, 8 divided by 2 can be worked out as log 8 minus log 2, which is 0.9030 minus 0.3010, giving us 0.6020. If we find the antilog of 0.6020, the answer is 4. Working with indexed numbers and roots. Consider 2 raised to power 3 times 4 squared. To work this out, we simply multiply the corresponding logarithms by the index. That is 3 times log 2 plus 2 times log 4. And the answer will be 3 times 0.3010 plus 2 times 0.6020, giving us the answer as 2.107. We find the antilog of that and we end up with 128. Now consider root 2 times cube root of 4. We simply divide the respective logarithms by the corresponding roots. That is, a half times log 2 plus a third times log 4, which will give us a half times 0.3010 plus a third times 0.6020. The answer is 0.3512, and the antilog of that is 2.2449. Let's take an example. Without using a calculator, find the following. In our solution, we first find the log of the numerator and then add them together. We then find those of the denominator function. That is, log 4.592 is equal to 0.6620. The log of 0.521 is 1 bar 0.7168. Log of 16.25 is equal to 1.2109, and we add all those logs and we get 1.5897. We then go to the logarithms of the denominator function. Log 3 cubed is the same as log 9, and we have 0.9542. Log 2.44 is 0.3874. Log 3.31 is 0.5198. Log 0.04 is 2 bar 0.6020. We add that and we get 0.4634. Since we are dividing the numerator by the denominator, we subtract the logarithm of the denominator from that of the numerator. That is 1.5897 minus 0.4634, giving us 1.1263. We are supposed to find the cube root of that. Therefore, we divide the log by 3, and we shall end up with 0.3754. Finally, we find the antilog of that, and we shall get 2.3737. You can try and confirm that answer with a calculator.
I love that math generally has initially clear and precise answers, that you know when you know it and you know when you don't know it. As you get farther on in it, the answers are not so clearly in the back of the book, but initially math has answers, clear answers. Sometimes they're hard to find, but that clarity. The second thing I love about math is it's a puzzle-solving kind of, if I can figure it out, and the joy of figuring it out, the kind of sense of accomplishment, the sense of excitement when you get it, the challenge of trying to get it. It's that puzzle-solving kind of thing that I really, really like.